Listo, y estamos de vuelta para darle la bienvenida a nuestro siguiente orador, Aaron Rinehart, conectándose desde Estados Unidos. Me dicen que ya tenemos a Aaron en el Zoom. ¿Sí? Producción lo está buscando. Aaron, how you doing? Thank you so much.
Hello. Hola.
Hola, ¿cómo estás? Thank you so much for doing this for our second year. One of very weighted keynotes here. You were a sensation last year, so we were so glad you are coming back this year. You have very interesting talks to share today. So I'm gonna let you do it. We do have a hybrid event, so we have people here on site that wake up early in the morning so they can be here and not miss your talk. And we do have folks that are on live. So what we're gonna do is after the event, it's in Zoom, so we can broadcast to other people the talk. And also after that, we're gonna have you jump in on hopping, go to the Rio Negro room, and then you're gonna have like a session, meet the speaker, ask me anything, I don't write hard questions. All right, so I'm gonna let you guys do it. Thank you so much, guys. The stage is all yours.
Thank you very much. Share my screen here. Oops. Sorry. All right. Well, thank you everyone for coming out to this talk today at DevOpsDays Medellín. This is actually one of my favorite events that I did last year. I'd also like to thank Carlos and the other organizers for putting on probably one of the best ran events I've ever seen. So I'm pretty excited to speak here. I truly believe this is one of the best events I've seen in terms of DevOps Days. So I'm going to go ahead and get started. So today I'm going to talk about chaos engineering as it applies to cybersecurity. So we call that security chaos engineering. I'm going to talk about how to navigate the complexity in modern software in terms of security using chaos engineering. So some of the things I'm going to talk about are the nature of complexity in software. Talk about chaos engineering, what that is. I'm going to talk about security chaos engineering. I'll also be talking about some of the use cases where you can apply the craft, the technique. I'll talk about a framework you can use in order to write chaos experiments for security. And we'll talk about the relatability of sort of the DevOps, Agile, and the SRE world, and how we've kind of come to this need for a technique like chaos engineering. And then I'm going to go into a few example experiments. A little bit about me. My background is I'm the CTO and co-founder of Verica.io. My co-founder is Casey Rosenthal, the creator of chaos engineering at Netflix. I'm most notably known as being the creator of security chaos engineering. I wrote the first open source tool in the space called Chaos Slinger. I'm a frequent author and speaker in the space. Prior to Verica, I was the chief security architect of United Health Group, the largest private healthcare company in the world. I also worked at a long background at Department of Defense in America, as well as NASA Safety and Reliability Engineering for space. It's a little bit about my background. You'll see my Twitter at the very bottom, at Aaron Rinehart. Feel free to send me a direct message. I love connecting with people. I love hopping on Zoom calls and chatting about the topic. So feel free to hit me up. Okay, so we're gonna dive right into the material. So what seems to be happening is no matter how much better we think we're getting at security and even availability and stability, it doesn't seem like we're really getting much better. I mean, you keep seeing headlines in the news, and we're constantly seeing outages, breaches, and incidents, and they're coming more often, and they're getting bigger in magnitude. So what is going wrong? What are we doing wrong? We're trying to do everything we can. As engineers, this is what we get paid to do: deliver value to market and keep our systems and computers stable, delivering that value. Well, the problem is it's that our systems have become so difficult to model model their behavior as humans. It's very difficult. They've evolved beyond our human ability to mentally model their behavior. And this is a characteristic of complex adaptive systems. Examples of complex adaptive systems are like, the weather, the financial markets, stock markets, where the international politics, bird patterns. Now our complex distributed systems are now complex adaptive systems. And one of the characteristics of a complex adaptive system is that humans cannot mentally model their behavior in their head. There's too many pieces. There's too many pieces moving and changing constantly. Well, the speed, scale, and complexity of modern software has made these complex systems that we're building, managing, and running more and more difficult to do so. So if you look at on the left side of here, this picture, you see what they call a Death Star diagram. You might have seen this before, but every dot you see, every small tiny dot you see is a microservice. Microservices were a great idea, but now they've just introduced a whole nother level of complexity and scale that makes it hard for us humans to keep track of what's going on. And this is the challenge. So where does this complexity come from, right? Well, everything you see on this slide, you see continuous delivery, DevOps, Agile, APIs, auto canaries, CI/CD, service meshes, circuit breaker patterns. Every engineer in the audience is saying, oh, these are good things, Aaron. Yes, they are. These are helping us deliver value to market to customer faster than we've ever been done before. The problem is that with the scale and its complexity that we're already dealing with, it makes it very difficult to keep track of everything and what's going on for any given person to do that. And that makes it difficult and challenging on the post-deployment world to know what's happening. You'll explain further here in a minute. So if you look at the right-hand side here, you'll see the new OSI model. Now it's just software. Software has officially taken over, especially from layer 2 of the traditional OSI model and upward. It's now pretty much all software that we're dealing with. What makes software really difficult is that it's easy to change it. There's a relationship between the easyability, flexibility, and rate, the speed of change, and complexity. And we're going to expand on that. So software, it never decreases in complexity. It only increases in complexity, because every time you change it, you increase the complexity. There used to be a saying in software that there still is a saying that in software that says there's no problem in software we can't fix with another layer of abstraction. The problem is these layers of abstraction are starting to cause problems at speed and scale. So, a lot of people will say, Aaron, this is a logical answer in your head. A lot of people will say, Aaron, if our system is complex, why don't you just simplify it? Well, there are two different schools of thought in there. So there's two different places complexity comes from. There is essential complexity and accidental complexity. Essential complexity comes from places like Conway's Law. Conway's Law states that organizations are destined to design computer systems that reflect the way they communicate as a business. So you can't change the complexity without changing the nature of the business that you're dealing with. So that's hard to do that. The other world is accidental complexity. Accidental complexity is the methodologies, like we talked about earlier, the methodologies and techniques we use as software engineers to build software. Well, a lot of people say or talk about making the system more simple, but to take a complex system and then to make it into a simple system, you would have to change it. If you remember, there's a relationship between change and complexity. So if you're going to make a complex system simple, you have to change it. You have to introduce change. So really, what you're doing. So the school of thought that people prescribe to really is that you're not simplifying, you're just moving complexity around the system. So what's more effective is actually to navigate it, become more aware of it, to derive more context through better instrumentation as engineers. And we can do that with chaos engineering. Chaos engineering is a new methodology for experimentation and instrumentation to learn more context about the system. So I'm sure you all have legacy systems out there, right? Well, legacy systems are usually, that means business critical. That means that the business needs that system, that it relies on it. It makes most of the money for the business. Well, these legacy systems have become known as simply stable systems. Well, what's interesting about that is that were these systems always so stable? And the answer is no, they were not. What we mean by stable is that engineers feel generally confident in that the system works the way they think it does. They feel competent, that they understand the tooling, the documentation roughly reflects what the system actually does. We understand the system. We feel comfortable with it, right? But it was almost never that way to begin with, right? We learned how what the system really was versus how it versus we learned what we thought the system was versus what the system actually was. We learned the reality of the system through a series of unforeseen events, surprise events, outages, incidents, but the problem with learning that way is that you learn through customer pain. The customer or engineers or the business had some sort of productivity loss as a result of that. We don't need to learn that way. I mean, that's how the system became stable over time, is those events. Well, chaos engineering is a proactive methodology to try to perturb the system or introduce faults in the system to try to surface failure that's in the system and fix it proactively. So another way of thinking about it is chaos engineering is the technique of proactively introducing turbulent conditions into a system or service to try to determine the conditions by which it will fail before it actually fails. So there is no pain. There is no loss of productivity. We're able to learn about the problems, fix them proactively. So it's not about breaking things. So part of the problem is that we forgot somewhere along the way that system engineering is a very, very, very messy exercise. And let me explain. So in the beginning, we love to think about the system like this. We've got the plan, we've got time, we've got resources, and we've got our code, our Docker images, we've got our GitHub, we've got our configs, we've got our software secrets, we've got staging, we've got prod, we've got QA, and of course, we've got a beautiful 3D Amazon diagram showing exactly what the system is, right? Well, in reality, the system almost never looks like this, okay? What happens is after we go live with the system, we start to learn about how the system really worked through a series of surprise events. Sound familiar, right? Is that the marketing team comes down and says, hey, we got the pricing model wrong. We need to refactor pricing. Or there's an audit that comes in from the government, or there's an outage on the payments API. We have to hard code a token, right? Or there's an expired certificate, or there's a DNS problem, or there's a code freeze. These things start happening. The reality of the post-deployment world is much more complex than we remember, but we just slowly drift into a state where we no longer recognize the system that we built. And that's why we start getting these unforeseen outages and events, is that the system has begun a life of its own post-deployment. So the problem is not with the CI world or the CD world per se. It's the post-deployment world that we're really trying to navigate. So in the end, our systems have become more complex and messy than we initially remember them being. So what does all this have to do with security? Okay, I'm getting to it. Okay, so as an engineer, cybersecurity is a complex context-dependent discipline. So as an engineer, as a builder, I've been a builder most of my career. Even before I got into security, I've been a builder. So as a builder, as an engineer, I need the flexibility and convenience to make changes. I have to make changes to a thing. My job is to deliver business value to a customer. So I'm constantly changing what I need to change in order to deliver value to customer via product, right? Well, security is a context-dependent discipline. You must know what you're trying to secure in order to know what you need to secure about it. So you need the context, right? So security is forced to do a stateful scenario, right? So so you go forth and you build a security based on your understanding at a point in time of the thing that's changing. The problem with that is that engineers are constantly building and changing the environment toward delivering customer value. Well, security, we designed it at the point in state. What's happening is that it's constantly changing. The environments are constantly changing, and the security doesn't know it needs to change until there's some kind of problem, or it can't phone. Security control can't phone home, or because there's a blocked port, or there's or you can't access something because IP address has changed, or something like that. We don't know there's a problem until there's a problem, and that is a problem. So really, the problem is there's no feedback loop between the two. With security-based chaos engineering, what we're identifying is the drift. Because we're introducing this condition that we designed for the system to ensure that it can still do what it's supposed to do. So I'll expand on that in a second. So chaos engineering, we like to break down instrumentation into two very loose definitions, okay? So testing would be the verification or validation of something we know to be true or false. We already know what we're looking for before we go looking for it. We're like in the security world, that's a CVE, that's an attack pattern, it's a signature, those sorts of things. But experimentation, we're trying to derive new information that we previously did not know. And that's why we call chaos engineering tests, we call them experiments, right? We don't call them attacks. Some people will call you'll hear people say that. That is wrong. You should not say it, call it attack. Security people will not like it if you call it attack, because we're not attacking the system. We're trying to proactively understand whether or not the security works the way it was designed originally. And that's not attacking the system. So how do we typically discover when our security measures fail? Okay, well, the problem is it's usually through some sort of footsteps in the sand. It's usually through a security incident launched through these footsteps in the sand. That's what John Allspaw likes to call it. Those are log events. Those are traces. Those are some sort of mechanism, observability mechanism telling us, hey, there's something weird going on here, right? And a security incident is launched. The problem with that methodology is it's reactive. It's after the fact, and it's very difficult to establish when it actually started. Attribution is very difficult to identify, especially if you have poor observability. So what we're trying to say here is that security incidents are too late. We must be more proactive in understanding the engineering of our systems, and that applies to security as well. So what happens during a security incident? Okay, I mean, what happens generally, right? Well, what happens is people freak out. Okay, they lose their minds, especially if you're not in security. You're worried about being the blame, name, shame game. Yes, it all rhymes, but that's what I call it. It's that you're worried about if you're saying to yourself, I knew I shouldn't have pushed that code, or you're saying, I knew there's a problem with X, right? And people are worried about losing their jobs, right? People are worried about being blamed for causing it, right? This is not a good learning environment, okay? We don't do chaos engineering here. We don't do chaos engineering here. There's too much going on. People are freaking out, okay? We do chaos engineering here, right? Nothing but rainbows and unicorns, right? When there is no problem, because we're proactively trying to ensure the system still does what we designed it to do, right? In this world, we're not worried about being blamed or the outage or the CEO getting on the phone saying, get that system back up and running. In this world, we're able to proactively look at the system in an objective way where we're not worried about that problem. Our brains are not overburdened with all that information. So we don't do chaos engineering here. We do chaos engineering here because we can learn better in this environment. Because it's about learning. It's about continuous learning. So chaos engineering. Okay. So the Netflix definition of chaos engineering is it's the discipline of experimentation on distributed systems in order to build confidence in the system's ability to withstand turbulent conditions. So another way of my definition would be it's the proactive way of introducing turbulent conditions or faults into a system or service to try to determine the conditions by which a system or a service will fail before it fails. Learn about the failure, discover the failure, find the failure before it fails, fix it so it doesn't impact customers or your delivery of value. So remember, chaos engineering is about establishing order, not about creating chaos. Don't think it's about breaking things in production. It is not about breaking things. You will lose your job if you go around breaking things. I guarantee it. It's instrumentation. It's engineering. Right? Okay, so there are 3 books I'd like to get your attention to. There's original Netflix Chaos Engineering Report that you can download from O'Reilly. There's also the Chaos Engineering main body. This is the main body of knowledge you need. I'll give you a link to download this at the end. There's also the Security Chaos Engineering O'Reilly Report. If you'd like to download that, there'll also be a link to that. And Kelly Shortridge and I are writing the main body of knowledge right now for security chaos engineering. So connect with me. I'd love to make sure you all get a copy of that at some point. Security chaos engineering. Well, just as a summary, it's not a whole lot different. It's the same principles and technique applied to security use cases or to security parts of the engineering of a system. So, okay. So 2 more things that I like to always say to an engineering audience is that engineers don't believe in 2 things. We don't believe in hope. We don't believe in luck. We believe in instrumentation, sensors, data. These are the things. Tell us if it works or doesn't work and why. Give us context so we can build something better. That's what we like. So hope is not a good strategy for engineering. It worked in Star Wars, but it doesn't work for us. Okay, so what we're trying to do is proactively understand our system and where its security gaps are before an adversary can take advantage of them. So I'm going to talk a bit more about this in a second, but one of the use cases for security chaos engineering is incident response, because the problem with incident response is your reactive is the problem with the incident response. And I'm going to expand on that. So the use cases. Right, so some use cases you can use security chaos engineering for. They are documented in this book, as well as I have lots of material I can point you to. But you can find that information in the books. But incident response is a great use case. The use case a lot of people start with is control validation, ensuring that security mechanisms actually do what they're supposed to do by introducing the conditions. Security observability is another one. So Prima Virani at Pinterest started doing this years ago with my work. She started turning off microservices, and their assumption at Pinterest was that when that happened, they would immediately detect that behavior. What happens is most people don't actually look at individual microservice logging. They look at log volume, and of course they missed it. Most people will probably miss that, but you're not going to miss 1,000 log events amongst 10 million or 10 billion. You get the idea, right? Another interesting aspect is compliance. Every chaos experiment, whether it's availability or stability or security, has compliance value. So make sure you keep that output. You can use that for compliance reasons. Okay, so for incident response, the problem with security incidents is that they're subjective. No matter how much money you spend $1 billion or you spend $1 million, it doesn't matter. There's no difference, right? You spend, or you have 1,000 people, or you have 100, or you have 10, or you have 1. No matter how many people you have, no matter how much money you spend, you still don't know a lot of things. You're hoping what you built and what you put in place actually prepares you for when something happens, but you don't know until it actually happens. You don't know where they're coming from, why they're trying to get in, who they are, what they're doing, and how they're going to get in. You don't know these things, right? Because you're waiting for an event to happen, right? Chaos engineering, we're proactively introducing these events. And now when you introduce the event, You have a point where it began. Instead of waiting for something to happen and identifying, oh, this log event, oh, it must have happened on this system and it started there. Well, no, we can actually start the event, and now we can manage and measure how effective the process was. Do we have enough people on call? Do we have good run books? Did they make sense? Were people available? Did we have the right skills? Did the technology work the way it was supposed to? Did we stop it? Did we prevent it? Did we detect it? Did we send good log data? All these things. So this brings us to Chaos Slinger. Chaos Slinger is on GitHub. It's somewhat of a deprecated tool, but I'm no longer at the company of United Health Group. But the tool, if you go there, it represents a good framework for writing security chaos experiments. Yet again, that is documented in this book on how to do that, as well as it's documented in the GitHub repo very well. There are 3 functions you need to write. There's generator, there's slinger, and then there's tracker. And those are the 3 functions, and you'll see those documented on the GitHub repo. But I'm going to talk about a bit about an example that we use for Chaos Slinger in the repo that will help you understand how and why and what we do for chaos experiments for security. So the example I'm going to show here is that for some reason, actually, I'll be back up here. So when we released Chaos Slinger on GitHub, we needed an example experiment that whether you're a software engineer, a network engineer, an executive, no matter what sort of role you're in, you kind of understand what a firewall port is, a network port is, and the problems that can happen with that. Most people understand those things, but for some reason, even in the cloud, we still have this problem of misconfigured ports and unauthorized port changes, even though we've been solving for it for 20, 30 years. Well, it could be that a software engineer didn't understand flow, a network flow. It's not as intuitive as you would think. It could be that somebody filled out a ticket wrong. It could be that somebody applied the change wrong. And that can happen as code, or that can happen as from typing as a human. It can happen in lots of ways. We're humans, right? We're fallible. Our assumption was in our AWS instances at the time is that when someone were to introduce a misconfigured port, that our firewalls would immediately detect and block that activity. It would not be an issue. This was what we believed from a security team perspective. So we built Chaos Slinger. We built an experiment that would proactively introduce an open or closed port to a EC2 security group that wasn't already open or closed. And what we were doing, we were using that to be a trigger event for this process. So our assumption was that the firewalls would immediately detect and block it, be a non-issue. So we went forth, we started running this on our AWS instances, and it turned out that only about 60% of the time that was true. So the firewalls only detected it about 60% of the time. This was due to a drift issue, a configuration drift issue between our non-commercial and our commercial software divisions. So easy. Remember, this was proactive. There was no incident. There was no war room. We figured out there was an issue with the firewalls and we fixed it. No problem, right? The second thing we learned is the cloud native configuration management tool caught and blocked it every time. It's like, wow, something we were barely even paying for was more effective at catching it than something we were paying for and using. So that was the second thing we learned. The third thing is that we didn't have what they call a security incident and event management tool. That's called a SIEM. You've heard the word SIEM. We built our own big data lake for security, where we did our own correlation and analysis of security events. And we were very new to the cloud at the time, and I wasn't expecting that would correlate an event when this behavior, because it's supposed to correlate an event from these log data from these two tools. And it actually did, though. So that's the third thing we learned, is that we actually the homegrown security logging solution actually correlated an event. So the event went to the SOC, the Security Operations Center. The security analyst in the Operations Center got the alert, but they couldn't tell which AWS account instance it came from. And as an engineer, you can say, well, Aaron, you can map back the IP address to figure out where it came from. Yes, you can, but that can take 5 minutes, 10 minutes, 15 minutes. That could take, if SNAT is in play, that could take an hour, 2 hours, right? If 1 minute of downtime is $10,000 or $1 million, it's very expensive. But guess what? Guess what? So remember, there was no incident. There was no problem. We proactively introduced this condition and we learned this. All we had to do was add metadata pointer to that alert, and the problem was gone. It was fixed. It wasn't a problem. No, there was no loss of revenue. There was no pain. Nobody was being blamed, right? We proactively were able to learn about this problem that we had and fix it. So that's kind of how the process works. And right here, here is the link to the Security Chaos Engineering O'Reilly book. You can download it from verica.io/sce-book, as well as here's a link to both books. I'll leave that up here for a little bit so folks can grab it. And thank you very much. I think we're going to turn in. Oh, I think we're actually going to open up for questions, I believe. I think, is it here or are we going to the next room? Okay. I will provide the link to folks in the queue. Oh, there you go. There's Carlos. Okay.
Awesome. So we have a question for the audience, and then he just want something. I'll let him know what it is.
I can hear you now.
All right, excellent. So we have someone coming in for a question. Is it? Over here. Right. Go ahead. Hold on.
Hi.
No.
Hi, Aaron. Thanks for the talk. Basically, it's I understand, and basically, it's a really cool idea, chaos engineering, especially in distributed systems. But basically, what's the difference between chaos engineering in security and pen testing? Because that was not really clear for me. Thanks.
Thank you. And I get that question a lot, right? So I will address all the differences in the question. So the question was, what is the difference between security chaos engineering and pen testing? I will also say, what is the difference between security chaos engineering, pen testing, red teaming, purple teaming, and breach and attack simulation? They're all kind of in that same similar spectrum. I'll explain that. So pen testing typically fits more as a technique in the red teaming world. By red teamers, there's red team exercises, and so red teaming used to be red teaming exercises suffered the same problem as DevOps, right? It used to be that red teams would attack and blue teams would be like, what's going on? What are they attacking? I don't know. So there's a wall of confusion, right? So red teams would come in periodically and they would attack the systems, and then they'd write up a report and say, okay, this is what all the stuff you did wrong, blue team, go fix it. So we were supposed to evolve from red teaming into purple teaming. Purple teaming was supposed to be the evolution of it, but now we're doing red teaming, purple teaming, pen testing. So some of the issues with pen testing, red teaming and purple teaming, is that one, they're not tuned to software that well. The value is in manual pen testing for software. That's where the value is, because you have to, if you're going to pen test software, you need to, if you're going to pen test Node, like JavaScript, you have to know JavaScript. Like if you're going to pen test Java, you got to know Java, right? So you have to really be very narrow and niche. And a lot of times, our pen testing, or red teaming, or purple teaming exercises are really only done on the top 5% at the most of the portfolio, and they're typically only done maybe once a month, once a quarter type of exercises, except for places like Intuit, who does Red Team Mondays. But so also, a lot of times with pen testing or with breach and attack simulation tools, they send a lot of data to a distributed system. And it's very difficult to ascertain what worked, what didn't, right? If you're doing a multi, let's say a Node.js multi, mass assignment attack, you're doing that on a Node.js server, right? You could be, you're sending so much data to the system. The goal is to try to get in. It's not try to figure out what's wrong, what's not. Like, so what we're doing, you could think about security chaos engineering as a difference between all those other things as failure injection, fault injection. What we're doing is we're introducing the conditions that the controls were originally designed for. It could be, so we designed a firewall to detect a misconfigured port. Okay, when that condition is introduced to the system, does it actually detect that event? Does it throw good log data? Does the log data make sense? And remember, like when we're dealing with microservices, we're not dealing with one server, two servers. We're dealing with 300, 3,000 things, right? It can get very messy very quickly for making lots of changes. So does that make sense? It's more, you can think, there's actually some great resources online. There's an article I wrote at opensource.com called Redfish, Bluefish, Purplefish, Chaosfish, though I break down all the differences. I can post that link in there. There's also, I have a whole section on that coming in the big book, because I get that question all the time. So I appreciate that question.
Okay, thank you.
Hey, no, thank you.
Actually, Aaron, can we get this breakthrough also a book that you have, Chaos Engineering from last year?
Oh, yes, we did. Yes, we did.
All right, so he just won a ebook from America.io. Well, tell us about the book.
We can send some real books too if you want to, Carlos. It's up to you.
All right, so we for any ¿cómo estamos en tiempo? Yeah, we're good in time. So, all right, yeah, show those books, guys. So we have people on the audience. If they have questions, they can earn these 2 books. Para las personas que están aquí, ¿alguien tiene alguna otra pregunta? Puede ser en español, yo la traduzco o intento traducirla. ¿Sí? All right. Yeah, for chaos engineering, do we have to do that manually all the time, or there are some automated tools out there or code that we can reuse? That was from the audience. Here.
Great question. That's a really great question. So there's some great open source projects out there. There's the Chaos Toolkit is great. You've got the Litmus Chaos is a good open source project. You know, there's commercial tools out there as well. But you know what? You don't really need any of that. You can do it all. You can do it with Bash. You can do it with Python. You can do it with Go. You know, so there are 2 different modes to chaos engineering. Okay, there's the experimentation phase. That's where you're running something for the first time and you're not sure whether or not the system's going to do what you think it's going to do. So you will, in that situation, you want to you want to run it and be careful and watch it. So that's the manual mode, right? The first time you run it. But once you run it, you're probably not going to be right, because you're introducing the condition you think the system is going to catch or to exhibit. Like it could be an SLO. You could be introducing 150 milliseconds of latency because your SLO is 200 milliseconds. You introduce 150 milliseconds of latency and find out that the system breaks, right? You have to figure out why, and then you fix it. Then you introduce the condition again manually, and you try to understand, if you're right, if it actually succeeds, then you run it then you go into the second mode. Then it's continuous. You run it like a regression test over time, if that makes sense. You can, and another thing people always ask me is, do I run this from the CI/CD pipeline? You can run it from the CI/CD pipeline, but just be wary of the fact that not all changes to the system happen from the pipeline. Meaning a network segmentation or configuration issue might happen outside of the build, right? And so the goal is really to run it all the time independent of the pipeline, but you can use a pipeline if you need to.
Right. Thanks, Aaron. Yeah, the guy is giving the thumbs up for the answers. There? ¿Y cuál es la? Right. From you. Thank you so much for the. I'm translating. Thank you so much for the talk. And from your point of view, what's the future of DevSecOps?
Wow. I have to admit, I've got some of the best questions at this conference. What is the future of DevSecOps? I would love for DevSecOps to be the return of engineering to security. We began a long time ago with security as an engineering problem, and we went off on this weird direction for a long time. And DevSecOps has brought a lot of security people back to the engineering roots. I would love DevOps, DevSecOps, Agile, XP, SRE. I'd love it to be part of just good engineering practices, right? Let's call it good engineering. I would love compliance to be a byproduct of good engineering, right? And I think DevSecOps has brought security people back into the fold, right? And I think it's important. I have personally been seeing more and more GitHub projects written by security people. You start seeing more and more code written. It's got to happen. When the whole stack is software, you can't have people in the flow of that who don't understand software. It's not going to work. Security people must understand software, or it's in Python. As a minimum, was written originally for children. I mandated at United Health Group, the largest healthcare company in the world, over 1,000 people to learn Python, and it was an amazing exercise. There's no reason why you shouldn't learn a little bit of code. So that's what I think the future is. I think as security returns to engineering, and we join the value delivery at a company.
Right, I got 2 thumbs up from the guys. Sorry, I was checking the chat, so I did not see any questions for you on the chat, but the fellows there, they're going to have the opportunity to talk to you on the Rio Negro, right? On the hopping. There's going to be somebody moderating that's going to help us with the English if you guys want to go meet Aaron Rinehart and convince you to give you one of the books that he has co-wrote. So thank you so much, Aaron, for being with us today. It was an amazing time.
Thank you, my friend.
Again, so we hope you in Medellin next year, but physically here, right? From this,
I would love that. I would absolutely love that.
All right, so see you in the Rio Negro, Aaron.